All right, so now we're into respiratory physiology part two. We've gotten the air in, we've done our inspiration, brought all that air down into that exchange surface, and now we're going to talk about how we get exchange of gases from the alveoli into the blood, and then how that's oxygen is circulated as well as CO2 in the blood. Because those are the two gases we're looking at. We're looking at getting O2 in, CO2 out. So we're going to be looking at the exchange and also how it travels through the blood, how it's carried. And so we'll be talking about hemoglobin and so forth. All right, so let's get started. All right, so let's look at the laws, and we got to look at what's called gas laws for that dictate the exchange of gas, because that's what we're going to be doing, exchanging gases between the air and the blood and blood to air, right? So gas laws, there is a pressure that is exerted by these gases. The gravity of the earth pulls in the air, pulls in these molecules, and there is a pressure that these molecules exert over a specific area, right? The total pressure is the sum of all the gases out here. The gas, our environment here, is not made up only of oxygen. Oxygen's only 21%. The big bulk of gas out there is nitrogen. But the total partial pressures of all the gases out here, CO2, O2, nitrogen, they create the total pressure. Okay, so the total pressure, that 760 millimeters of mercury that we have out here, the pressure, is the sum of all the partial pressures from those different gases. And what's going to dictate the movement of where gases go is similar to concentration gradient. We saw solutes dissolved in a solute or solution. They'll move from an area of higher concentration to an area of lower concentration. In this case, gases will move either singly or a mixture from an area of high pressure to an area of lower pressure. So if I have a higher partial pressure of oxygen over here and a lower partial pressure of oxygen here, the oxygen is going to move towards the area of lower partial pressure of oxygen. In this case, it's singly. We're moving from areas of high oxygen to area of lower oxygen. Okay, but the term is partial pressure. That's what's going to dictate the movement, not concentration, but partial pressure of the gas. Here it's kind of showing those partial pressure of gases. If we were at sea level and the air was dry, okay, and we're at about room temperature, 25 degrees, all right, we can see the bulk of the air is made up of nitrogen. 78% times 760 would get you that partial pressure of nitrogen of 593. Okay, and you'll see the partial pressures. You'll see PO2, PN2. All right, depending on the gas, will be there. You can see carbon dioxide, very small amount of partial pressure there. One thing I want you to notice here also, as when we heat the air and we add water vapor to it and 100% humidity, you can see what happens to the partial pressure of oxygen. It decreases. And if you remember, as we move air into our alveoli, we heat it and we add a water vapor to it. So you'll see that the partial pressure of the air is actually not the same as the partial pressure when we actually get the air into the alveoli. It will be actually lower in partial pressure when we get there. Right. Let's see, as pressure decreases, as altitude increases, why this takes place. You can see the atmospheric pressure. All right, and if you multiply this by 21%, you can see we get even lower and lower partial pressure values. This is why remember, our gradients as we go from, we decrease the difference in gradients, the amount of diffusion is less. So when we're at sea level, we have a higher partial pressure, and say this is the level of oxygen in our blood, there's a bigger gradient. But as we move in elevation, right, what happens to the partial pressure is it goes down, and therefore that gradient, the difference between oxygen in the blood and oxygen that's reaching the alveoli, the gradient isn't as great, and so we don't have as much diffusion of oxygen, and that's why it's harder to breathe in these higher altitudes. Why does this take place? Why is the atmospheric pressure decreases? Well, think about it. It's gravity is pulling. It is stronger nearer to the Earth than it is further out, and so the pull is greater, and so there is more gas molecules creating more pressure. Okay, but that's what's taking place. This is why our oxygen is decreasing as we go up into higher elevations. And if we do this, we're decreasing the gradient, and we're going to see it's going to affect the exchange of gases. So since partial pressure is going to dictate the exchange of gases, let's look at the air that actually reaches the alveoli. When we get to the alveoli, we can see O2 has dropped a bit from the environment in that we have 105 millimeter, and actually you'll probably see it more written as, with quiet breathing, it's 100. And the CO2 was up. Remember, the CO2 is getting released into the alveoli, so there's a higher concentration of it, or higher partial pressure of it, and so there's roughly about 40 millimeters of mercury. But what you'll see as blood is returning, say here's the alveoli, as blood is returning, the partial pressure of oxygen in this blood that's returning to the lungs is going to be lower in partial pressure than what's in the alveoli, lower than that 100, and therefore oxygen will leave. The CO2 content of this blood returning to the lungs will be higher in CO2, higher than this 40 millimeters of mercury, and therefore CO2 will leave the blood and go into the alveoli. Right, so that's going to be the driving force for this exchange of air. Okay. But one other facet we got to throw in here is we're going from an air environment into a liquid environment that is non-compressible. So we're going to see that the solubility of the gas also determines on how much gas. Even though partial pressure might be the same, the concentration of the partial pressure in air compared to in liquid, say in the blood, is going to be different. Okay, so movement of gas into the air into a liquid. We're going from air, the alveoli, into a liquid, and we're talking gas, determined by pressure gradients. But then the other big factor is the solubility of gas in the liquid. Okay, and temperature. Okay, but let's look at solubility of gas. Okay, and what we're going to see is CO2 is very soluble. What do you have when you in that Coke? With Coke, you have lots of CO2. Okay, what we're going to see, so with low partial pressures of CO2, we can have more CO2 dissolving into the gas, or into the liquid, sorry. In O2, we're going to see is a lot less soluble than CO2. So that's going to change actually concentration. I can have 100 millimeters of mercury of gas, partial pressure here, and 100 here, but we're going to see the concentration is higher here than it is actually in the gas because of the solubility of that gas into the liquid. Right, so here is our O2 in water. Okay, gas, you can see that, get my big head out of here. When you're looking, we have 100 millimeters of mercury and 0 here in the liquid, and you can see some of that oxygen dissolves in, but even at the same partial pressure, the concentration is different because of that solubility. So oxygen is not very soluble into a liquid. So that's a problem because what are we dissolving into? We're dissolving into blood, right? We'll figure out how are we going to make this work. I'll give you a hint when we talk about hemoglobin. Okay, but here is that exchange. So even though we're at 100 here, and we're going to see the blood returning is actually at 40, so we're going to have very little that will be dissolved into that liquid. Whereas here we can see the difference between our oxygen we see here and PCO2 at 100, and at 100 same partial pressure, you can see there is not as big a difference in the actual concentration of the gas because CO2 is very soluble in water. This is going to come into play in how we transport these gases in the blood. Okay, CO2 is very soluble, so it can be dissolved in the blood, where O2 we can dissolve very little in the blood. So how do we usually carry O2? We're going to see hemoglobin. If we bind it to hemoglobin, now it's not in the blood, we can continually load up that hemoglobin. All right, so there's where the differences are going to lie a little bit in the transportation of the O2 and CO2 once we get it exchanged, dissolved into the blood. All right, so let's look at the actual gas exchange. How are we getting diffusion of gases? Right, diffusion is going to lie on the difference in partial pressure. Where there's a difference in partial pressure, the gas is going to go from an area of higher partial pressure to an area of lower partial pressure. And we'll see the blood returning, the blood that has dropped off its oxygen to the tissue, right? When it reaches the alveoli, the blood that are in that capillary beds that are wrapping the alveoli is roughly around, in quiet breathing, is roughly around 40 millimeters of mercury. As it passes this exchange surface, we have 100 millimeters of mercury compared to 40, and O2 is going to go into the blood. Now we're at a partial pressure of 100. That blood returning, right? It's going back to that left atrium, to the left ventricle, and then being pumped out to the tissue. We'll see when we get to the tissue, what has the tissue been doing? The tissue's been taking in the oxygen to do cellular respiration and creating CO2. So we'll see when we reach the tissue, all right, it's somewhere around 40 millimeters of mercury because the oxygen has gone into the tissue. It's being used in creating cellular respiration and forming the CO2. So there are lower levels of oxygen at the tissue, and now we got that blood coming through the capillaries to the tissue. We have an area of higher partial pressure to an area of lower partial pressure, and the oxygen is going to get unloaded to the tissue. All right, and then we return back. We're at about 40. We return back to the lungs to load up our blood with oxygen again. Okay, in the opposite direction, let's start at the tissue. The blood coming to the tissue has a partial pressure of CO2 of 40. The tissue's been there. It's been doing cellular respiration, creating the CO2, and so there is a higher partial pressure of CO2 at the tissue. All right, this blood reaches the capillary beds at the tissue. We have a difference. We have 46 compared to 40, and so CO2 is going to move into the capillary beds, and then we'll bring that blood back to the lungs. And what we see at the alveoli, Partial pressure is 40 millimeters mercury. The capillary beds that are wrapping alveoli is at 46, and the CO2 will leave and move into the alveoli because of that difference in partial pressures, that gradient in partial pressures. Okay, so that's the movement. Right, that's how we get the exchange. Remember this surface, what was it? It's very thin. There's very little fluid between the two surfaces, and therefore we can get this rapid diffusion of gases. All right, so before we move into, we get the gas exchange, and before we move into how the gas is circulated throughout the body, let's look a closer look at the pulmonary circulation. We took a quick look at this in cardiac, but pulmonary circulation is that circulation that is basically the right side of the heart. We got the right atrium, right ventricle, and then up to the lungs, and then back to the left atrium, back to the heart, and then we get the systematic. So we're looking at the flow of blood through this region here. And what we see, if we remember correctly, or remember from cardiac, is that we put out about 6 liters of our cardiac output. At rest is about 6 liters of blood per minute. All right, but that blood, again, is being pumped out, and it's being pumped out throughout the systematic circulation throughout the body. So we got all this blood pumping through, 6 liters, and what we see is this right side of the heart has to match the left side. So we have to pump 6 liters of blood through here, but you can see the amount of vessels. We're not pumping out throughout the body, we're just pumping up to the lungs and back to here. So we need to flow the blood through here very quickly. All right, and so that makes it that this right side here, okay, has to be high flow. Okay, the output on this right side, even though it's only going up to the lungs and then back to the heart, is it has to match the left side. So it has to match roughly that 6 liters, or when we're exercising, even greater amount, right? So we have to have high flow through here. It must be flowing through there very quickly. All right, and so to get that high flow, we're going to see that we need to have low pressure. Okay, the arterial pressure is very low compared to the systematic. Right, that low pressure allows us to push it through. There's very little resistance, and we can push through. Right, that gives it low resistance, and now we can move blood through there very quickly. We can have that very high flow. All right, so low pressure, high flow allows us to match the right side with the left side of the heart. Okay, and you can see that here. You can see the difference between the systemic and the pulmonary circulation. Okay, running from the arterioles to the venules, you can see the difference, much lower in the pulmonary circulation, and that allows us for this high flow. Okay. And one other factor we want to regulate in the pulmonary circulation is the perfusion of blood into around the alveoli. So what we're going to see in our lungs, all right, ventilation is not always uniform. It's not always all uniform across. There are areas that our ventilation is greater, where there is more oxygen. And so what we want to do is we want to match. All right, we got the alveoli and we have the capillary beds that wrap around them. We want to match the perfusion of blood around those alveoli that are well ventilated. Okay, again, not all areas of the lungs are as ventilated as greatly as others. And so we want to match where ventilation is greater. So where ventilation is good, we want to dilate to those capillary beds that surround the alveoli that are well ventilated. So we want to match what we call ventilation in the alveoli to the perfusion of blood into the capillaries around the well ventilated alveoli. Right? So we're moving the O2 in, and to get gas exchange, we want a blood flow past the alveoli. Okay? Must be high enough to pick up the O2. So again, we're going to want to match the ventilation. Okay, ventilation with perfusion are matched. So areas where alveoli are low ventilation, lower O2 content, we're going to constrict. All right, we'll constrict the vessels there so we won't perfuse a bunch of blood out there where there's low O2. We want to perfuse the blood where there's high amount of ventilation around the alveoli that are well ventilated with well oxygen. Right, and you can see that match here. And what we've seen, this is opposite of what's seen in systematic arterioles, because where tissue has low O2, we want to get O2 to that tissue. So we'll actually dilate the arterioles to tissue that is low ventilation or has low O2 content. This is the opposite when we come to the pulmonary. We want the alveoli that are in low O2 to not perfuse around it, not send a lot of blood there, but alveoli that are well ventilated, yes, we want to perfuse blood to them so we can pick up that oxygen. Okay, you can see here, reduced alveolar ventilation. So there's low O2. You can see the alveoli is not round and well ventilated. What will happen is the capillary beds will be, the arterioles will be constricted, and we will send less blood through here because we have less O2 to pick up. But where we have enhanced alveolar ventilation, all right, nice big round alveoli, well ventilated, we got high O2, and what are we going to do? We're going to dilate the arterioles to perfuse around there so we can pick up the O2. So we match, okay? Wherever the O2 is high, we're going to match with the perfusion so we can pick up that oxygen. All right? That's one way we're matching. Also, another area of regulation is we can regulate the ventilation. We can regulate our breathing rate. We can regulate how deeply we breathe. Okay, and what are we looking for? We have chemoreceptors. Okay, this is going to be a reflex. We want to keep our O2, we want to keep our CO2 and O2 contents within a homeostatic range. All right, and so we have to have sensors for this. Our sensors are chemoreceptors. Right? They pick up changes either in O2, CO2, or in pH. We're going to see that CO2 levels can regulate pH. All right? We're going to see that in a bit, but CO2 levels go along with pH levels and then also O2 levels. Okay, what we're going to see in these chemoreceptors, right? We have some chemoreceptors in the aortic arch and the carotid bodies up here. All right, and then also the medulla have receptors that respond to changes in pH. What we're going to see here with more of our sensors are going to be, ventilation is going to be regulated more by CO2 or pH rather than O2. Okay, and we're going to start heading into this direction, so let's just think about our solubility of our gases. Which one was more soluble in water, into fluids? That's the CO2. So we will have more CO2 dissolved in the blood compared to O2. What we're going to see is our O2 is going to be bound. Very little is going to be dissolved in the blood. Our O2 we're going to see is going to be bound to our hemoglobin. So our chemoreceptors can respond more quickly to changes in CO2 rather than O2, because this doesn't change as drastically because most of it is bound to O2, where changes in dissolved CO2 in the blood will have a more varying effect, and also we'll see pH will vary more greatly because it's regulated by CO2. All right, so our breathing, how quickly we breathe and how deeply we breathe, is more regulated by these two factors rather than P, our partial pressure of O2. All right, so sensitivity, hypoventilation. All right, you can see, boom, hypoventilation means low ventilation. Right, you can see we get a large change in CO2. Normal ventilation here, and hyperventilation, we get lower levels of CO2 because we're expelling it more. Okay, this is more drastic change here than what we'll see in oxygen because they are bound to that hemoglobin. Right, and I didn't want to draw this out but here you can see how our CO2 affects what? Our pH. Because look at our teeter-totter. If this starts getting high, all right, we hypoventilate. If we hypoventilate, we're going to retain CO2. If this level starts going up, which way is my equation? This side starts getting heavy. Which way is my equation going to be drawn? It's going to be pushed in this direction. Right? Normally I keep this at a certain level. All right, somebody's choking me out and I'm hypoventilating. I can't breathe. I can't rid myself of the CO2. I can't expel it. The CO2 levels are going to get high, and what's going to happen to my blood? If I'm drawn and pushed in this direction, we can see that's going to increase the levels of protons, and what's going to happen is decrease in pH. All right. So you can see how CO2 can regulate pH. If I went the opposite direction, I went hyperventilation, that would draw the equation this way. And what would happen to my pH in that? My pH would go up with hyperventilation. So hyperventilation is up. Hypoventilation, my pH will go down. Right? So this changes more drastically these levels in the blood. And therefore, typically what regulates our ventilation is our CO2 levels, or pH of the blood is going to be the bigger draw for regulating how deeply I breathe and how quickly I breathe. Those are two factors in breathing that we can affect. How quickly? That would be a hyperventilation. I increase my breathing rate. Or hypoventilation, very slowly. Or I can also breathe more deeply, get the O2 in, get more CO2 out, or I can breathe more shallowly. All right, but you can see what happens if I hypoventilate. I breathe less or stop breathing. My CO2 levels are going to go up because I'm not expelling CO2 as regularly. Or when I hyperventilate, what's going to happen to my CO2 levels? They are going to go down because I'm expelling them more quickly. So here are kind of the regulation. Here is the reflex. Here's how we keep homeostatic. Is we have chemoreceptors for CO2, right? We have chemoreceptors for O2 and pH. But again, the bigger draw is going to be pH and CO2 on my ventilation. Okay, those send the information, either they're at the medulla or those carotid and aortic chemoreceptors send via the afferents to the medulla, and this is where we have our respiratory centers. And our medulla and our pons are going to regulate via somatic motor neurons. Okay, they're going to cause effects on external intercostals, the diaphragm, scalenes, all those muscles that control ventilation. These somatic motor neurons can control how deeply I breathe. All right, if I want to breathe deeper, what do I need to do? I need to recruit scalenes and sternocleidomastoids. All right. Whereas if I want to expel deeper, I need to do the internal intercostals and abdominal muscles. All right, and those will either cause me to expel more or inhale more deeply, exhale more deeply, and also if I control the rate of these, I can also control the rate of ventilation. But the draw is the CO2. Okay, we're going to see CO2. If CO2 levels get high, that means my pH levels will be getting low. And what's the response going to be? It's going to cause me to kind of hyperventilate, because that will allow me to expel CO2. Whereas if CO2 levels are low, say I was hyperventilating, that will cause me to slow down, breathe less shallowly, and that will help bring my CO2 levels back up, right? But that is the draw. We'll see emotions, voluntary emotions, right? Stress, if we get very scared, all right, our limbics can have an effect on, we usually have a faster breathing rate. Or if we're stressed out, some people hyperventilate, can't slow down, right? And so there is some conscious control or emotional control over some of the breathing rate. But the actual non-voluntary effects are going to be regulated by what chemicals are found in the blood, by those chemoreceptors. So now that we've controlled kind of our breathing rates, let's look at the exchange and how the oxygen is carried around in the blood. Okay, if you remember, oxygen is going to diffuse into the blood, but remember that oxygen, it is not very soluble. The solubility into a liquid, into the blood, is not very great, and so there's very little oxygen that is going to be soluble. So how do we keep oxygen coming into the blood? Okay, if we bind it to something, it's not in the blood, and so we can continually dissolve. That'll allow us to dissolve more oxygen in. And so when we look at the total oxygen content in the blood, there's the oxygen dissolved in plasma. But again, remember, that is small, but it's going to be controlled by how much oxygen is in the air. More oxygen in the air, usually at lower elevations, okay, compared to altitude, that'll allow more oxygen in. How much ventilation we're doing. Deeper, higher ventilation, we're going to be able to dissolve more oxygen in. And the surface area and diffusion distance, as long as we keep that minimal distance between the alveoli and the blood, the capillaries, we can get more distance, right? So if we keep the amount of interstitial fluid and the thickness of the membrane to very minimal, we'll allow more oxygen in. And then also surface area. The more we're able to ventilate and have more oxygen across the surface area, we can get more diffusion. And then we saw our perfusion of blood. We want to perfuse the blood out to the regions, those alveolar regions that are more well ventilated. Okay, this will control oxygen dissolved in the blood. But where is most of the oxygen held? How is it going to be brought around in the blood? How do we continually bring in lots of oxygen? It's because our oxygen, the bulk of our oxygen, is going to be bound to hemoglobin. That's the HB here, the hemoglobin, right? And you can see the saturation. We're going to see hemoglobin can bind 4 molecules of oxygen. And what's the percentage of saturation? Okay, is chiefly controlled by how much dissolved in plasma. Right? We dissolve more in, we can bind more to hemoglobin, and we're going to get more saturation. Also, our saturation is another factor, is the total number of binding sites. How many red blood cells do we have? If we have more number of red blood cells, okay, or if we have more hemoglobin per the red blood cells, we're going to be able to bind more hemoglobin, and we're going to have a greater amount of oxygen bound to hemoglobin. Okay, we're going to look at some factors that affect the saturation also, besides the oxygen dissolved in the plasma. The factors that affect oxygen dissolved in plasma, we're going to see there are these factors here that help control the saturation of O2. Okay, but the takeaway here is very little oxygen dissolved in blood. There's going to be most of our oxygen is going to travel through the blood bound to hemoglobin. This is where the bulk of our oxygen is found in our blood. So here's kind of a good rendition of showing you where oxygen lies in the blood. You can see in the plasma how very little is 0.3, less than 1 milliliters per 100 milliliters, whereas in hemoglobin, we got 20 milliliters of O2 per 100, right? So the bulk of the oxygen is going to be carried in the blood by hemoglobin. And this is key because remember this low solubility of oxygen. If this hemoglobin wasn't here, we would be stuck with this very little amount of oxygen. But as we diffuse oxygen in, it binds to hemoglobin, and that allows us to diffuse more oxygen in. Okay, but again, the bulk is here bound to hemoglobin. So since hemoglobin is going to be carrying most of our oxygen, let's take a look at this molecule. All right, there are 4 globulin polypeptides, so 4 subunits, 4 proteins make up this hemoglobin molecule. And you see in adults, we'll have 2 beta chains and 2 alpha chains. All right, and in each of these subunits, protein subunits, there is this heme. This is a structure here, and in the middle of this heme is this iron molecule in which we get the binding of oxygen. Okay, so for each of these hemoglobin molecules, we can see we can get 4 molecules of oxygen bound to it. Right? And when oxygen is bound to the iron heme, it's called oxyhemoglobin. And when it's not bound, it's called deoxyhemoglobin. Right? And there's another one called carboxyhemoglobin. Right? And this is when carbon monoxide, we'll see carbon monoxide can bind to this heme group. All right, we will also see that some carbon dioxide will bind to hemoglobin, but it won't bind to this actual heme. It will bind to an outer surface of the hemoglobin molecule. All right, so this is where carbon monoxide and carbon dioxide differ, in that carbon monoxide is going to actually bind, and the carbon monoxide will bind with what we call a higher affinity, bind tighter than the oxygen, so it actually will replace the oxygen. Some of you might have heard carbon monoxide. That is when people go into a park, go in a garage, start the car, carbon monoxide builds up, and what carbon monoxide is basically silently choking you out because it is basically offsetting the carrying capacity or the oxygen carrying capacity of hemoglobin, and therefore you're not able to get the oxygen to the tissue. All right. There is a term called percent oxyhemoglobin saturation, and this has to do with the total hemoglobin available, how much is actually bound to oxygen. All right, and what we're going to see at their lungs is basically 97% saturation. 97 normally at the lungs. 97% of the hemoglobin is bound to oxygen, is in the oxyhemoglobin form. Okay, and we're going to see how this operates. One thing you got to realize with this is we bind oxygen here, but this binding has to be reversible. Right? We want oxygen to bind to hemoglobin in some, but at other points we want hemoglobin to release the oxygen so the oxygen can go to the tissue. So we have to have this reversible bond, and we're going to see this bonding can differ under differing conditions, but the ability of oxygen to hold on to hemoglobin is called the affinity. If you have a higher affinity, the heme will not want to release oxygen and will bind tighter and hold on to it stronger, whereas if there's a lower affinity, it's more willing to release the oxygen. Okay, and we're going to see how this takes effect as we move through and change characteristics of the blood and see how that affects this affinity for oxygen. Okay, and so that is called the loading and unloading. We don't want to load deoxyhemoglobin. We want to bind oxygen. All right, and then we want to be able to unload, release oxygen to release that oxygen to the tissue. Okay, and what we're going to see is the direction. The loading and unloading is determined by the P, the partial pressure of O2 in the environment. Okay, we're going to see in high oxygen environments, there's going to be a higher affinity and further bond strength to bind oxygen. When PO2 is low, there's low PO2 in the environment, okay, hemoglobin is going to be more willing to unload the oxygen. So in high O2 environments, it's going to load, bind with higher affinity to to oxygen, and at lower PO2s, partial pressures, it's going to be more willing to unload the oxygen from hemoglobin. Okay, so this is where we get this reversible bond, and one of the main factors that controls whether we're going to load or unload has to do with PO2 in the environment. High partial pressure of O2, we're going to load, it's going to bind the higher affinity to hemoglobin. All right, whereas in the low partial pressure of O2 environment, hemoglobin is more willing to release or unload oxygen. Right, and this is what we can see here in this oxygen dissociation curve. All right, if we look here, we have partial pressure of O2. All right, here is the percent of oxyhemoglobin saturation, how much of hemoglobin is bound to oxygen. What was our oxygen content? When we get to the lungs, our partial pressure of O2 is at what level? Right? It was at 100. Okay, and what do we see? How much of the hemoglobin is saturated with oxygen. How much oxyhemoglobin saturation do we have? We are up here. We already used that term, 97%. Okay, but look as we move down in partial pressures. Okay, how much saturation is there? When we reach the veins, if you remember the partial pressure at the tissues, at the arterioles, or at the capillary beds, was roughly around 40. And how much of the oxygen or hemoglobin do you see bound to oxygen? Now we're down to roughly 74%. Okay, so we went, this here tells you how much oxygen was unloaded from when we went to the arteries and now to the arteries to the veins. That means in between here is the capillary beds, and you can see how much oxygen is released or unloaded. All right, so in a normal environment, roughly we're going to drop from 97 to 74, so we drop off about 23% of what was bound to hemoglobin. We release or unload. Okay, there are some factors that can affect this unloading. Okay, there are factors that will affect it that will make oxygen or hemoglobin bind to oxygen more, and therefore it will be more resistant to unloading. And there will be factors in the blood that can change and make it so that there will actually be more unloading. There will be a lower affinity for oxygen, and the hemoglobin will be more willing to release or unload the oxygen. Okay, so we're going to be able to shift this curve either right or left, and we're going to see how that affects the unloading of the oxygen. Okay, one of those factors that can shift or affect the unloading of oxygen is pH, also called the Bohr effect. Okay, we'll see when we become more acidic, when the pH decreases. Okay, looking at this graph here, you can see the partial pressures. I'm going to get my big head out of the way. Partial pressures of O2 are here. And here's the hemoglobin saturation. Okay, and what do we see? The middle here is 7.4, so that is your your homeostatic blood levels around 7.4. What happens when pH decreases? Right, you can see 7.2. We get what's called a right shift. We're moving right from the normal curve. Whereas if pH increases, becomes more alkaline, we get a left shift from the normal curve. Let's look at how this affects unloading. Let's look at where we are at 100 and 40. What did we get when we were here in the normal curve? We're 97 and roughly, where are we at here? 74. Okay, so we got about 23% of unloading of oxygen. Let's look at our 7.6. At 100, we're all the way up at 100% saturation. And where are we at when we get to 40? We're at roughly 85. So let's say there's an unloading of about 15%. What's this tell you? All right, when it's more alkaline, now is hemoglobin more willing to release oxygen? No, it wants to hold on. It's not releasing it. We were able to release at 23% at 7.4, but now at 7.6, the same partial pressure of 40, we were only releasing about 15%. So hemoglobin at higher pHs has a higher affinity and is more reluctant to unload the oxygen. Okay. Here we got 7.2. Say we're up here, we'll say roughly 95% saturation. And when we get to 40, where are we at? We're at probably about 62. So 62 minus 95, we're at 33% of the oxygen was unloaded. So what's this tell you? At a lower pH, a more acidic pH, there is a lower affinity for oxygen. Hemoglobin has a lower affinity for oxygen and is more willing to unload. Okay, the way I want to think this, and many of the factors we're going to see, think about what's going to happen if you exercise. If you exercise, do you want to supply more oxygen to your tissue? I would say the answer is yes, right? You want to be able to give more oxygen to the tissue. So you want hemoglobin to be more willing to unload oxygen so it can unload the oxygen to the tissue. And what happens when we exercise? What happens to our blood pH? We create more acids, we create more CO2, our blood becomes more acidic, and therefore our hemoglobin is more willing to unload oxygen. Okay, so this pH is one factor that's going to affect the affinity or the saturation. It's going to affect the curve, give us a right shift or left switch, depending on what's happening to our pH. Another factor that can affect the affinity of hemoglobin for O2 is temperature. Here is normal temp at 37 degrees. What happens when we get warmer? We get a right shift. When it gets colder, we get a left shift. And where do you see there's more unloading of oxygen? We have more unloading of oxygen when the temperature is higher. When the temperature is lower than normal blood temp, all right, there is less unloading. Again, I'm using the analogy of exercise. What happens when exercise? Your core temperature is going to go up some. Probably not to 43 degrees, but it's going to go up. And so what happens when you want to exercise? Do you want hemoglobin to be more willing to unload oxygen? Yeah, because you want to supply those tissues. And what happens when we get warmer and we're exercising? That creates an environment that allows hemoglobin to release more oxygen, supply those tissues. Okay. Right. Now we have one other factor called 2,3-DPG, 2,3-diphosphate glycerate. Okay, it is formed as a side reaction to the glycolytic pathway, glycolysis in red blood cells. Red blood cells only do glycolysis because there are no mitochondria, there's no organelles in our red blood cells, so they do glycolysis. All right. Oxyhemoglobin. When there is a lot of oxygen bound to hemoglobin, this inhibits the enzyme for the production of DPG. Okay. If there is lower oxyhemoglobin, all right, there's less saturation of hemoglobin, we will form more 2,3-DPG. Okay, what happens? Increased 2,3-DPG. Again, the middle curve is normal. Okay, no 2,3-DPG. Oh, wow, look at that. There is a very, very high affinity. Oxygen without DPG, hemoglobin does not want to release or unload oxygen. But if you add more 2,3-DPG, You get a right shift, and oxygen is, or hemoglobin is more willing to unload oxygen. Okay, again, when will you have lower oxyhemoglobin? When you're utilizing lots of oxygen, such as when you're exercising, right? You're going to increase your 2,3 dBg when you exercise, and what's that do to your hemoglobin? It allows your hemoglobin to release more oxygen. Okay, there is a lower affinity. Okay, so these are the factors. We can get these right shifts or left shifts. Right shift is going to say, hey, unload, hemoglobin's going to have a lower affinity for oxygen and more willing to unload it. When there's a left shift, oxygen is going to, or hemoglobin is going to want to bind more tightly to oxygen and is not going to want to unload it. It's going to have a higher affinity, less likely to unload the oxygen. So let's look at some instances when this affinity for oxygen by hemoglobin is important. One of those cases is fetal hemoglobin, because where's a baby get its oxygen from? It's from mom. And so mom's hemoglobin has to release the oxygen. All right. And so if the fetal hemoglobin was to pick up the oxygen, if it had the same affinity as mom's, when mom released it here, it wouldn't be bound or wouldn't bind to hemoglobin, or hemoglobin wouldn't bind to it because the affinity would be the same. So fetal hemoglobin has a higher affinity. So it can carry the oxygen. So it can pick up the oxygen that mom leaves. So when mom unloads, her hemoglobin unloads it because of the higher affinity here at the same partial pressure, the fetal hemoglobin will bind to it. And why does it do this? Remember we saw it was alpha and beta chains. There's a gamma chain isoforms, and these chains do not bind that 2,3 dBg. And remember, if you don't bind 2,3 dBg, you get a left switch or left shift. All right, and that's what's happening with the fetal hemoglobin. It has a higher affinity for oxygen at the same partial pressures of O2. All right, so fetal hemoglobin has a higher affinity than maternal hemoglobin at the same partial pressures. Here, partial pressure, higher affinity for the fetal hemoglobin. All right. Another case of this is myoglobin. Myoglobin is in the tissue. It's not in the blood, it's in the tissue, in the muscle tissue, and myoglobin is a resonant binding of hemoglobin. So when oxygen levels go low, there is this level of myoglobin. So in case oxygen levels go low, this myoglobin here can release some oxygen to sustain the tissues for this lack of oxygen. You know, only can do it for a certain amount of time, but it is there as a safe hazard in case there is low oxygen level. But you can see, same case as similar to fetal hemoglobin, in that it has a higher, myoglobin has a higher affinity for oxygen than hemoglobin does. You can see at the 40, much higher affinity. So what would happen is myoglobin wouldn't really release oxygen until we get to these low partial pressure, when oxygen levels are low. Okay, when there's hypoxia or low oxygen, then the myoglobin will release and can stay in the tissue for a certain amount of time. Okay, we'll see cardiac muscle actually, when it contracts in systole, there is a period in which there is no oxygen coming to the tissue. So it goes in low oxygen, and the myoglobin will release oxygen to sustain it until the next systole. Okay, but the key is that the myoglobin has this higher affinity, otherwise it would not pick up oxygen when hemoglobin released it. All right, so now we're done with oxygen. Let's look at how carbon dioxide is transported. Okay, carbon dioxide is actually transported in 3 ways. Remember, carbon dioxide is more soluble in water, so one of those ways is dissolved in plasma. It is the least amount, but it is at 10%. Right? Carbon dioxide can also bind to hemoglobin, called carboaminohemoglobin, right? And that's 20%. But remember, the carbon dioxide, unlike the carbon monoxide, does not bind to the heme. It binds to an outer area of the protein, not actually at the heme. Okay. The main way in which carbon dioxide is transported is via bicarbonate. It is converted to bicarbonate and it travels through the blood, and then it will be converted back to CO2 when we get to the lungs. Okay, we will see red blood cells contain carbonic anhydrases that catalyze the formation of carbonic acid. So we get converted to water and CO2 to carbonic acid, and if you remember what happens to carbonic acid, as it will be converted to protons and HCO3 negative, or bicarbonate. All right, and so that is, we're going to convert that CO2 to bicarbonate, and then it will travel through the blood as bicarbonate, and when we reach the lungs, it will be converted back into CO2. All right, so let's look at this process. All right, so on this slide, I want you to reverse these arrows. They should be going in this direction out of the tissue because CO2 is getting converted. All right, and the tissues we're making CO2 at the tissue, and what do we see? The CO2 leaves the tissue. Okay, roughly 10%. I know your book says 7%. CO2 is dissolved in plasma. All right, 20 or 23% combines to hemoglobin to form carboaminohemoglobin. Remember, this CO2 is not binding to the heme, right? It's binding to an off-site location in that protein, okay? An allosteric region of the protein. Okay, and then here is how we're getting. Remember, most of the CO2 that is formed is going to be converted to bicarbonate. And so this process in which the conversion of CO2 takes place in the red blood cells is called the chloride shift. All right, so the chloride shift takes place at the tissue, and that CO2 entering the red blood cells. Again, there's carbonic anhydrase. The enzyme is in the red blood cells that converts CO2 in water to carbonic acid. As CO2 levels increase, we push the equation in this direction. And if we push in this direction, that carbonic acid is going to be converted to proton and bicarbonate. All right. Deoxyhemoglobin. That's what we would have. We would have more deoxyhemoglobin at the tissue because we've released the oxygen from the hemoglobin. Okay. Deoxyhemoglobin binds to, it likes the protons. Remember, we're forming protons and bicarbonate. So the protons will actually bind to the hemoglobin molecules. Therefore, this is gone. Now we're left with bicarbonate. As we continually convert to bicarbonate, the bicarbonate levels in the red blood cells will get high, and so high bicarbonate here, lower bicarbonate outside the cell, bicarbonate's going to leave. But as it leaves, it takes with it its negative charge, and therefore makes this positive environment. And to offset the positive charge, the chloride shifts in with its negative charge. So this is where we get the chloride shift. Chloride shifting in as bicarbonate is leaving the red blood cell. Okay, so the chloride shift takes place at the tissue. All right, what happens when we go up to the lungs? We're going to get what's called the reverse chloride shift. All right, oxygen is loading. All right, CO2 is leaving, put this direction, CO2 is leaving. Okay, oxygen is loading. So now we're converting, we're getting deoxyhemoglobin to oxyhemoglobin. Okay, oxyhemoglobin, unlike deoxyhemoglobin, does not like the protons. All right, and what happens is the protons get released from the hemoglobin in the red blood cells. That draws the bicarbonate back in. As the negative bicarbonate comes in, the chloride shifts back out, and now we go in reverse because the CO2 levels, CO2 is leaving into the alveoli, and so that draws this equation into this direction because the CO2 is continually being diffused out. So we get the conversion of bicarbonate and proton to carbonic acid, and now we go in reverse direction, and that carbonic anhydrase is going to convert carbonic acid into CO2 and H2O, and as we convert to CO2, the CO2 is getting diffused into the alveoli and expelled in the air. Okay, so the reverse chloride shift takes place here at the lungs, at the alveoli. So we've kind of alluded to how this CO2 affects pH levels. All right, so remember we have our buffers. We have our carbonic acid and we have our bicarbonate out there, and that's going to help buffer our proton levels and therefore regulate our pH. Okay, that is our first line of defense in pH. But you can see we could also regulate CO2 levels. CO2 levels could help us regulate pH, because if we increase the amount of CO2 in the blood, all right, we have a normal level of CO2 where we keep homeostatic, but if our pH starts going up or starts going down, we can help offset that pH by either retaining CO2 or expelling more CO2. So you can imagine if our pH went up, we could increase our CO2 levels in our blood, and that would make it more acidic and therefore would offset the pH. Whereas if our pH of our blood was lower, more acidic, okay, retaining CO2 makes it more acidic, so now we would want to decrease CO2. So you see how we can offset this. Okay, we're going to see the lungs and the kidneys are going to be able to work in relation. We're going to look at the kidneys again in urinary, but these two, lungs and the kidneys, help regulate pH balance in the blood. Okay, we can have ventilation changes can affect pH. If I have inadequate ventilation, if I'm not able to expel as much CO2, there are diseases in which I can't expel as much, or say somebody was choking me out, I could get respiratory acidosis. Okay, acidosis means my pH in my blood is low. Okay, more at a pathological level, getting into a range that is non-homeostatic. Right? This pH And respiratory means the acidosis comes from the levels of CO2. In this case, CO2 levels would be high. Okay, excessive ventilation decreases CO2. All right, so I can get alkalosis because if I have lower levels of CO2 than normal, right, again, the levels of CO2 give the effect the alkalosis is coming from the levels of CO2. In this case, the CO2 levels are lower. Okay, we can see our kidneys. We're going to see these later on urinary, but what do you think the kidneys would do if they could secrete excess here or produce more bicarbonate? All right, for acidosis, what might we want to do? We want to secrete more protons and produce more bicarbonate. Whereas in alkalosis, we could actually rid ourselves of bicarbonate, and that would help offset the alkalosis. All right, there is another form of acidosis. I could get metabolic. And metabolic, where the changes or the disruption lies, has to do with the bicarbonate levels, not the CO2 in this case. So bicarbonate levels are not in homeostatic range. All right, if I have low bicarbonate levels, I'm going to get acidosis, and because it's from the levels of bicarbonate, it is considered metabolic, not respiratory. Right? Too much bicarbonate would sop up more protons, could make my blood alkalosis, and again, it becomes metabolic because where is the deciding factor? It's not CO2 levels, again, it is from bicarbonate levels in the blood. Okay, so respiratory CO2 levels, metabolic is bicarbonate levels, and depending on which one, okay, they're basically opposite. If I have too much bicarbonate, I'm at alkalosis. If I have too much CO2, I'm in acidosis, and vice versa. They are in opposition of each other. Right, and you can see that opposition here. This is the pH of my blood. 6.1 by the log. Not so worried about the log, but look at the relationship. Here is bicarbonate levels, and here is CO2 in the denominators. So if my CO2 levels go up, my diameter is increasing, and I'm making this lower, and so my pH would be lower. But if my bicarbonate levels went up, the numerator is increasing, and what would happen to my pH? It would go up. So going by this equation, you can see these are in opposition because one's in the numerator and one is in the denominator. Okay, but we can see how these two levels can help regulate our pH. All right, and we're going to see this again when we look at urinary. Okay, so if I want to keep this in range, I keep a certain level of bicarbonate in the blood that is homeostatic and a certain level of CO2 in the blood that is homeostatic. But what happens if my levels of CO2 go up? How could I keep this ratio equal? If my CO2 levels go up, I would need to increase my bicarbonate levels, so this ratio would stay equal, and I would get an equal number here, and my pH would stay regulated. Okay, so CO2 levels go up, I want to increase my bicarbonate. CO2 levels go down, I want to decrease the bicarbonate in my blood. So how do I keep this ratio in line? Depends on if one changes, I need to change the other. in the same direction.